So this is not going to be about macros or splitting. It's pretty different. Okay. So let me tell you about some work that we've been doing with these Italian guys, with Giuseppe, Giacomo, and Fabio Patrizi for the last couple of years. This is a journal paper that appeared in AAAI last year. So I'm going to give you a little bit of motivation, what the problem is, the composition problem, and two techniques, so 3 and 4, two techniques that are in this paper, okay, and some related work around that paper that is not in that paper, okay? So the motivation of our work is we imagine an environment where we have installed there, available some set of devices, okay? Some set of artifacts that are already there, that you got it off the shelf. You cannot change them, but you know the logic of them, okay? But you know, these are available already in your environment. This is a smart house, a smart environment, for instance. You can have video cameras, robots, you know, automatic blinds, microwave, whatever. But really, you don't want that, right? So the user doesn't want that. The user wants some other device, right, that is not available, that you cannot go and get it off the shelf. So you cannot buy it, but that's what you would like to control. The user would like to control that bigger and more complex device. So the task is basically, can we do this? Can we get a controller, right, that actually pretends that you're executing the home system by coordinating these available behaviors, we will call, or these available devices in the environment. Okay, so that's a motivation example. But you know, this motivation example in the smart environment could also be, you know, seen as web services. So we are coordinating web services. So you don't have, you know, blinds or microwaves. You have web services, and you want another web service. This is well known already in the web service composition area. Or it's robot ecology. So there are a lot of robots, very simple ones, and you would like to have some more bigger, more complex behavior that is not available. Or these devices are actually plans in an ancient programming language, and you want a bigger plan, a more sophisticated plan. And of course, it's related to automated planning. It's a sort of planning, a strange kind of planning when you synthesize these controllers. So if you, technically, we model this as transition systems, actually as non-deterministic transition systems. And we imagine, for instance, in this scenario, we have a set of available transition systems. This is like an entertainment room, right? And this is the target module, right? What we call the target module. This is what the user wants. Okay, so imagine the user wants to be able to first, you know, enter the room, turn on the light, then probably, you know, watch a movie or play music. After that, you may want to, you know, play a game, you know, play in a Nintendo or PlayStation, listen to the radio or browse the web, and then once it's finished, you will stop, turn on the light, and leave the room. Okay, but you don't have that device. You have these 3 devices, these 4 devices, right? You can have a movie device, you know, PlayStation, whatever. And you need to basically be able to guarantee to the user that you can play this entertainment room system. Okay? And notice that the devices could be incomplete, could actually be non-deterministic. So, for instance, when you are here, right, and you want to browse the web, you could go to either A2 or A3, and A3 is kind of an error state. And this allows you to model incompleteness of your devices. You may not know all the logic of your devices. Okay? So this is actually something that you need to tackle. So for instance, suppose that the user is requesting to turn on the light, of course the delegation will be to the light device, so you have a light device, and so you will move there, right? And then the user could request, you know, to play a movie, and then it will go to the movie device up there. Okay? So the question here is, can we actually guarantee the target module to the user, or we can't? So this is the problem statement formally. You know, it's like, you know, it looks like you're running the target module, but you're not. Right? But it looks like you're running the target module in your environment. And formally, okay, I'm not going to go into details, but we define, you know, what a controller is. And a controller is very simple. It's a function that takes a history of what things have happened in the system, all the requests and all the delegations, and the next action. Okay, so this is the next action that the user has requested, and it will give you the index. Okay, so you need to activate. You want to take a picture. Well, in this situation, you need to use that camera. Okay, and the composition problem basically means you want to synthesize a controller C, this function, such that this C has a property that realizes fully your target. Okay, but now put realizes in quotes because what does it mean? Well, it means that it realizes all the traces that T could do, right? All the traces that this target model can do. using these available behaviors. And more precisely, what it means is that this function C can always delegate all the legal requests of the target, always. So no matter how the target evolves, right, by the user requesting, this C will always give you an I, and this I will be okay. Now bear in mind that these available behaviors are non-deterministic. So you need to consider all the possible ways that these available behaviors may evolve, when you activate. You may take a picture on a video camera and the hard drive may get full, right, suppose, and then you will see that with a light in the system. So the composition problem itself, one thing we prove is EXPTIME-complete, So it's a little bit harder than planning itself. And it is no surprise because it's kind of a conditional planning or a planning under non-determinism, right? So there should be no surprise. So how do you solve this? What techniques can you use? We started a long time ago, before this paper, using PDL, so propositional dynamic logic, satisfiability. So you will encode the whole thing into a PDL theory, and you will do SAT there, Now you will do SAT, and then you will extract from the model the controller. Now the good thing about this, why we started with that, because PDL has this finite model theorem, which means that you will get a model that is finite if there is one, and so you can extract the controller from there. And that because there's this relation between propositional dynamic logic and description logics, you could potentially use ontologic reasoners to extract that if you get the model. Now you get one controller from here. Did you have a question, Carmen?
So you compile to SAT, Giuseppe complete problem, and you start with EXPTIME-complete problem. So what do you give up on the way?
Yeah, so the model will be exponential.
So description in SAT will be
exponential. Exactly.
Okay.
Exactly. So now this is not what we did in this paper. What we did in this paper, because actually the motivation was, but we really don't have any really reasoner, description logic reasoner that would actually give us the model. There are good, commercial description logic reasoners, but we don't have anyone that gives us the model. So we use simulation-based techniques at 30 games, but we also, some other people have done search, and we did last year planning one. Now let me tell you about these two. So simulation is a very formal notion in computer science. Basically means that one transition system can mimic the other transition system. So this state can mimic this state. Basically, whatever the other guy does, I can do it, and this property gets propagated in the future always. So I'm not going to go into detail, but this is a relation, it's an algebraic relation, and it's very well studied from the 70s. What we did here is we extended, the idea is this. Well, this problem, this composition problem, is the same as if all the available behaviors are able to mimic the target. So if you can capture that, that's fine. So we generalize the notion of simulation, what we call the ND simulation, so non-deterministic simulation, which basically means that at every step you can always mimic the target, right? So the available behavior can mimic the target, and this property is propagated no matter how non-determinism happens to be. And that's the theorem that says, composition basically amounts to having a simulation or an ND simulation between these two systems. And the good thing about this is that we get what we call the controller generator for that. If you get the larger simulation relation, you don't get just one controller. You get all the controllers in one structure, all of them. And this is pretty good because then you have flexibility when you execute, and you have some very nice properties on failure. So if for some reason some behavior dies or changes all of a sudden the state, you could still keep going or try to keep going with a minimum effort. So you can react to failures or you can refine your solution. Or for instance, you get another module. So somebody install another camera. You may be able to do more or more ways. Another way, I'm not going to go in detail here, is that to recast this as a game, as a two-player game problem. So you have some players, right, that play an infinite run, right? And what you specify the problem is an LTL formula, but to win the game. So you can only control the output variables, and the environment does the input variables. So this is so the synthesis is to actually compute a function f that is a strategy to win the game. And you win the game if you can guarantee that any sequence, right, any run will satisfy this LTL formula. Now LTL is well known to be very, very high. It's double exponential time, but we rely on some results on GR1 formulas are actually safety games, right? They are simpler, which tells you that you're going to play a game for formulas of this sort, right? Where there is an implication, the left-hand side is the assumption on the systems, and what things you assign? Well, what things you assume? You assume things like, the user will only request what the target logic says, right? And that there will only be one request per time. These are the things that you assume. And what's the requirement? Well, your requirement is very simple, is that you will never get stuck, okay? And stuck is a proposition that says the user is requesting an action that no available behavior can do at this point. So, and you don't want that. So it's a safety constraint that you don't want to break. And if you realize this, right, so then you get the composition problem solved. The interesting is not double exponential, it's polynomial, right, on the size of the formula and the game, but when we take all the available behaviors and we take the cross product of them, you get an exponential transition system, right? And that's why it still, of course, cannot be better than exponential. So it's optimal with respect to computational complexity anyway. Okay, and we can use them for these, game solvers, right? Like NuGet or ANSUS or ATL, for instance. We can also do this with ATL, alternative temporal logic. Now, these are two techniques that appear in the paper, and all the theory about how do you refine when failure happens. We also did with Miguel Ramirez last year with planning. Okay, so well, this is a planning problem. It's a planning under, with non-deterministic actions. And we used Christian Mu's PRP planner, and the task there is to find a strong cyclic plan. Okay, and it's quite tricky how to do this because here the interesting is there's no goal. Okay, there's no goal. The goal is to keep going, right? The goal is to never stop, to always be able to satisfy the user. So you need to do a planning without a goal, okay, without an explicit goal. And the way you do this is to basically your goal is to find a lasso, right, in the transition system, a very strong lasso. Okay, and we use Christian, as I said, PRP, and it worked pretty well as well. The latest thing that we've been working is what happens when there's no solution. When there's no solution, you don't want to say, well, sorry, you cannot do the target. You would like to have something more, right? So for instance, in this case, there's no solution. But there's something that you can do. You can do this target, for instance, which is a subset of this. Okay, maybe you cannot do web browsing or you cannot do movie. But of course, there are many sub-targets, right? Yep. So, and we proved that there is one that is unique and is the largest. So the Supremal is pretty surprising result that there's one that is the largest if you put all the realizable targets together. Anyway, so the conclusion is, this is the AAAI paper. We define the problem specification, the complexity, two techniques through composition and games, and some robustness property on how you refine the solutions. There's more feature work on adding data to here, or under-specified targets when the user doesn't know exactly what he wants. Okay, thank you for that. Thank you.
Time for one, maybe two questions, and otherwise you can take it in the coffee break.
So one comment, one question. The comment is there's a really nice trick introduced by Lipvetsky, so on and so on. The ICAPS work of the last time, and it's for the lasso. You can do a nice little non-deterministic trick for these infinite plans where it leads to an OK state and non-deterministically to a not OK state that still satisfies the goal. And so you need to find your way back to that spot where, again, you can achieve your LTL goal. So you're able to get these infinite loops, and you don't need to explicitly decide the lasso point, which is really bad for PRP.
This is the work from Neer and Hector Geffner?
Yeah.
That's actually what we
That's the lasso trick that you use?
That's what we use.
Okay.
Yeah, but for non-deterministic.
Good. And the question is, or half question, half comment, for the unplannable cases, PRP produces not monotonically increasing, but gradually better and better solutions, and it will spit out some Supremal, not the Supremal, but some controller that will represent what it is that you want. So it'd be interesting to see how close to the Supremal controller it actually produces in the end.
Right.
Even though there's no solution, it will give you a best solution it could find.
Right.
Yeah.
Can you go back to slide 10?
To slide 10.
Okay. One before maybe, where you talked about, here, this one, I didn't understand this issue of unexpected failures and adapting to them.
Oh yeah, that's a good thing. This is one of the nice results. So suppose that you are running the thing. So you have the composition, right? So actually a structure that tells you, yes, here's the controller, right? We call it a controller generator because it includes all the controllers. Now suppose that you're running this and for some reason you expected, some camera to be in some state, and that camera is gone, it's broken.
And that is not taken into account in your already non-deterministic model?
No, the non-determinism says that when you do this action, you will be in this state or in this state. But now suppose I tell you, you don't have this behavior. You cannot delegate to this behavior anymore. It's gone. Somebody, it broke.
Okay.
So the non-determinism is always...
So it's beyond the original non-deterministic model.
Yes.
The position you did not model.
Exactly. You did not model, right? Okay. You did not model.
And you can adapt to that.
You can adapt to that. Of course, there will be cases where you say, well, if you don't have this camera, you're gone, right? You cannot do it anymore.
Of course.
Yeah, if you cannot adapt. Right, but this will give you some very nice properties on if you can adapt, you don't need to do the whole thing again. I mean, the usual, what you can do is to just recompute the whole composition again. Yeah, but you don't want to do that. Yeah.
Okay, I think we need to close the session now, so let's thank Sebastian again.
Thank you.